Art Wiggins. Welcome to the next episode of The Art of Physics. And boy, have we got some physics for you today. Oh my goodness. One of the favorite topics that many people have about physics is magnetism. And magnetism is the one we're going to do today. And we have as our guest somebody who is quite magnetic in himself. This is Joe Lowry. Joe, welcome.
Thank you. I appreciate you inviting me here today.
Hey, he's magnetic. See what I mean already? Joe is going to show us some things about magnetism, because magnetism is not the easiest thing in the world because you can't quite see it. There are other aspects of physics you can see real well, but magnetism needs a little help, a little demonstration help. And Joe has brought along some goodies today to show you the magnetic field at its best. What are you going to start with?
All right, well, maybe the best thing to start with is a definition of magnetism. This is what physicists would define as magnetism. And it is a phenomena related to magnetic force. And it is what we call an action at a distance force.
Those are scary.
They are. Well, they're intriguing and confusing to a certain extent. Most of the forces we're used to are contact forces. So if I want to lift this up, I have to physically touch it. But gravity is an action at a distance force. If I let it go, the Earth will pull down on it, and it doesn't need to be in contact.
Right.
So magnetism is one of those action at a distance forces. Physicists describe the mechanism by which it works using magnetic fields. In the case of magnetism, or gravitational fields in gravity. We can show you an example of magnetic fields using what's called a magnetic field projector. And it's just a membrane that has oil in it and some iron filings. And if I hold it in front of a sheet of paper, I got to shake it up a little bit to get those iron filings kind of distributed around.
Physics likes to shake up people. You ever notice that?
We do. We only like to keep the status quo at bay. So if we hold the field or the magnet behind this, you can kind of see these magnetic field lines starting to develop, where the iron filings are aligning themselves with the field.
Wow.
So there's one example. Now that's a two-dimensional profile of the magnetic fields, but fields are three-dimensional. Oops. Get those separated. Three-dimensionally, so if I put this magnet, which is called a cow magnet, by the way, inside of here, hopefully we can see the field is three-dimensional, so it surrounds that magnet in all directions.
Joe, why is that a cow magnet?
Well, interestingly, this is what they put inside the first chamber of cows. Cows, not being bred for their intelligence, tend to eat pretty much anything that they come across on the ground, and sometimes that's chunks of metal. And the way the cow's stomach works, there's multiple chambers, and food is passed from chamber to chamber, and if they swallow a piece of metal, that could damage one of the chambers or multiple chambers, so they inject this little cow magnet inside their first chamber, and if they happen to eat any metal, it sticks to that and doesn't harm the cow afterwards.
As long as it's iron, it would work.
Exactly, exactly. If they're eating chunks of aluminum, well, we got another problem to deal with. But
right.
So that's the three-dimensional view of a magnet, of the magnetic field. All right, so again, magnets, as most of us have discovered at a very early age, they do a couple things. They both attract and repel. Now they only attract and repel certain materials. The most common is iron, and then we have things like nickel and cobalt, which are also attracted by magnets.
But lesser. Iron is probably the best, isn't it?
Iron is the best, yep, absolutely. But as we can see, these two magnets are stuck together because their opposite poles are towards each other. And if you pull them apart, and these are pretty strong magnets.
By the way, did the camera catch the twitch that those magnets had? Just when you pass those other magnets nearby, did you see them twitch?
Yeah, so again, another example of an action at a distance force. They can affect each other from a great distance. And these two magnets, if I have opposite poles, they will attract each other. If I have like poles and try to put them together, they don't want to be together at this point. And again, these are pretty strong magnets. I have to be careful putting them back together again.
Did those fit on either side of your hand? Did I see you do that once?
Yes, actually, these are what's called neodymium magnets. These are what
I'm just doing this and making him take them apart again.
Yeah, get my workout here. So these magnets are what's inside your hard drives. Also inside the little, I'm going to cheat.
The little earbuds?
The little earbuds on your iPods.
Just tiny ones that...
Yes, very tiny ones, which is, wow, I can't even get it apart anymore. Hang on. There we go. But yeah, these are pretty strong, and I can hold one on one side of my hand and it'll go through the hand. Of course, they come in much bigger and we'll go through more, but thicker things. But yeah, so again, these are...
Could you put them on
These won't work. I do have one set of these that are big enough that I have a friend who once did that through his head, and I'm not sure that's a good thing to be doing, but didn't seem to affect him much. So those are what's called a rare earth magnet or a neodymium magnet.
Wow.
Now, a little history of magnets, I think, is probably a wise place to start with. Magnets were discovered in a place in Asia Minor, and they were discovered at least 2,000 years ago, perhaps even longer. And they were naturally occurring little rocks called either lodestones or magnetite, named after the area of the world where they were discovered. I don't know if I have... Well, I don't have anything small magnet, like paper clips, but if you take a compass needle...
I had some.
Did you? All right. Well, even without that, with a compass needle, you can see that, well, not this one, not on that angle.
Oh, I've lost my paper clips.
Yeah. Well, this is a naturally occurring magnet. It is a lodestone. Ah, there they are. They were hiding from us. All right. So... can use this to pick up iron filings, and this was something that was discovered by the Greeks several thousand years ago. Another interesting discovery was that if they suspended this rock from, say, a small piece of string or twine or whatever they had back then, or floated it on top of something that was easy to float, it would align itself in one orientation all the time. One side of the rock would always point to the north, and one side would always point to the south. They called that north-seeking end the north end of the rock, and the south-seeking end the south end of the rock, which, as we'll see in a little bit, has resulted in a little bit of an interesting conundrum, if you will, when we defined the Earth and its magnetic field. So that was the original discovery of magnets. They were... really started to get its use for us around the 11th century when the Chinese began using it for direction finding.
Ooh.
And as early as the 12th century, perhaps a little earlier than that, the Chinese were using it for navigation purposes. The magnets came out, we discovered them a long time ago. An interesting corollary to that is it wasn't until around the very early 1600s that it was discovered that the Earth itself is a magnet. So about 400 years ago, we figured out that the Earth was a magnet.
What must they have thought when these rocks aligned themselves? What do they think was making the alignment if they didn't think about the Earth's magnetic field, I wonder?
They had, well, what I have discovered in reading is they had two different theories. One is that it was attracted to the pole star, so Polaris. Or the other one...
That's where pole got its name.
Perhaps. The other theory that I read about was that at the North Pole of the Earth there was a large magnet sitting there, they thought, and that's what it was actually attracted to. Interesting that it took so long for them to figure out that the Earth itself was a magnet. And actually I had an instructor, oddly enough, with the same name as you do, that once told us a story about Einstein and a compass. And I'm trying to remember that story in its entirety. I believe it had something to do with his uncle giving him a compass when he was very young, and I believe sick, perhaps.
It was actually his father.
Oh, was it his father?
His father,
okay.
And he gave, yes, indeed, absolutely correct. He gave him a compass to play with because he was a sick little child at the time. And Albert, if you're watching, I'm not trying to put you down in any sense. It was just a temporary thing. Don't get excited. It's all right. But he was sick for a while. And so his dad gave him his pocket compass to play with, which was probably a nice thing to do if you have a sick child.
Sure.
So he did that, and young Albert was fascinated I thought, wow, what is this? Anyway, action at a distance. I mean, he experienced it when he was like 5 years old.
All right.
So, nice way to go.
So yeah, so again, compasses fascinated most children, I think, or at least it did me when I was growing up, how they worked and just the magic behind them, which turned out not to be so much magic as physics.
Well, magic and physics, I think, are related. By at least some people think that.
Sure. I guess you could think about it that way. So we have this magnetic field that we now understand that surrounds the Earth, and it offers us protection as well as gives us a means of navigation. This magnetic field basically acts as a shield.
So what is it shielding us from?
Well, two things mainly. The solar wind, which is charged particles and particles coming off of the sun, and cosmic rays. The solar wind is constantly being produced by the sun and hitting the Earth as well as the other planets.
The sun is really pretty sloppy, isn't it? It's always putting out a bunch of stuff.
Yes, yeah. And then every once in a while it has an explosion basically on the surface of the sun called a coronal mass ejection, where we get lots of high energy particles coming off the sun.
Right.
And with that, there is some inherent risk involved, and that is, we lose communications, networks, satellites, things like that, but also what happens on the Earth itself. Now, those particles aren't extremely dangerous for living beings, but what they do, without the magnetic field around the Earth, they would be striking the Earth's atmosphere and essentially be eroding that atmosphere. In fact, if we look at Mars, Mars's atmosphere is much less thick or intense than our own. It's a weaker atmosphere. And that's due to this erosion from the fact that about 4 billion years ago, Mars lost its magnetic field. The core of Mars solidified, it cooled off and solidified and no longer has a magnetic field.
So the atmosphere is pretty necessary for us, of course.
Absolutely.
And so the magnetic field helps that.
Helps to protect that.
Yeah,
and the cosmic rays, which I mentioned, are from the galaxy itself, and these are harmful to tissue, living tissue. So us, and this magnetic field helps deflect those. One of the neat side effects, I guess you could say, or neat consequences of having this magnetic field is that these charged particles that do strike us from the sun, they get trapped in the Earth's magnetic field. They kind of spiral around these field lines that you see, and they start to move inward towards the polar areas, so the North and South Pole. As they do that, they have high energy and they strike the molecules in the atmosphere, the nitrogen and oxygen, and this causes those molecules to glow and give off light. Sort of like the fluorescent light tubes in our houses, except that the excitation mechanism is a little different.
Otherworldly.
Yes.
Excitation.
Exactly.
Wow.
And it causes this light, the atmosphere to glow, and you get these curtains of light called the auroras. And
I think we have some videos of those. David, can you show us an aurora video and let's see what that will look like? Because people there we go. That is the aurora borealis, as a matter of fact. And that's the one which is around the North Pole. And it's a video that shows how dynamic it is. That's really going, isn't it, Joe?
Yes, it is. It's amazing to see. If you have an opportunity, I encourage you to go out and avail yourself of it, because it's like no other show you can see.
Right, it's free.
Yes, it is.
Those are the best kind. Now that's the one near the North Pole, which is called aurora borealis. I think we have another one too, if we can get the other one racked up and showing. The other one is actually called the aurora australis, and this is at the southernmost pole. And this is from the space station, the ISS, and you can see this from space, which I think is really especially fascinating. Did you see that one, Joe? Did you ever see that one before?
I did, actually. I got to see the link to that, and it is incredible to see from space.
Yeah, from space. Wow.
Yeah. And actually, we have video footage of the auroras on other planets as well. So we're not the only planet to have a magnetic field, and so we're not the only one to have the auroras as well. So that's kind of exciting to see. Now, of course, we humans use magnetic fields for navigation, but we're not the only ones. There are animals that also migrate that use the magnetic field for navigation purposes. Birds, certain birds, and of course turtles are another one. And I was reading not that long ago that cows and deer, if not worried about too much, just kind of hanging out, relaxing, will typically align themselves north and south.
Oh.
And they think that has to do with magnetic fields as well, because if they're parked underneath those high voltage power lines, which disrupt the Earth's magnetic field in that local region, they don't align themselves north and south anymore. So it's it's a theory that they do that.
Do you think that's why homing pigeons home? Did they use magnetic fields in their homing?
I believe that that the pigeons are one of the birds that use that.
Wow, interesting.
Yes, it is. It's fascinating that we're not the only ones that use that.
Well, part of the reason this was all brought up, in my mind at least, was the fact that I was reading an article recently that said that the Earth's magnetic field is diminishing.
Yes.
And so what's going to happen with that?
Yeah, so I think it's interesting to understand how the Earth's magnetic field is generated. And it's, we have this planet that we live on, which is solid, but internally it's not. We have actually two cores, an inner core and an outer core. The inner core is a solid, very high density, very hot. And then the outer core is liquid, lower density and lower temperature. And of course the Earth spins on its axis around a pole, the north geographic pole and the south geographic pole, so it revolves around that axis. And because it's been rotating for a very long time, the fluid inside that liquid core has begun to rotate with it. However, there's also another mechanism that's occurring inside there, and that is the rolling motion associated with sort of like boiling a pan of water on the stove. So we have this convection current in there.
Sure.
Being that the inner core is hotter than the mantle above it, so the magma starts to roll inside there, and it's the result of all this motion that creates this magnetic field.
Oh, wow.
So if we go back about 1819 rather, there was a physicist named Hans Christian Ørsted.
Ørsted.
Yes, that discovered that there is a relationship between magnetism and electricity, and it was sort of an accident that he discovered it. He was getting ready to give a talk on about this new invention that they came up with called a battery. And he was testing his battery before the talk, and when he hooked it up, there was a compass needle sitting on the table, and the compass needle swung in a different direction. So he realized that a current passing through a wire created a magnetic field. And I can sort of demonstrate that with one of our electric magnets. If I take these two and put them together, this is just a piece of iron, and this one is a coil of wire that's wound up in there. And currently the battery is not hooked up. So there is no magnetic field associated with it, and so it doesn't hold it together. But once I attach the wire to the end of it, now there's a current running through there. Now, in theory, hang on, I don't think it was positioned properly. There we go. I think my battery might be getting a little weak, but
it's not the battery this week. It's Joe who's strong. That's what's doing it.
That's what I like.
I think it's all the working out, Joe.
Yeah. So the battery must be getting a little tired because it is holding together, but it's not as strong as it normally is. And if I take the wire off, of course, it falls apart. And I was playing with this the other day, and it was able to support my weight.
Yes, I saw him do that.
Yeah, when the battery was fresh, it would be able to support my weight. So creates a very strong magnet. Using a little electricity, and it's just a D battery. So inside the Earth we have this core, this liquid core that's in motion, and it's made up of mostly iron, nickel, and cobalt, which the motion of that fluid is what creates this magnetic field around the Earth. However, because this fluid isn't rotating at the same rate as the Earth does, and because the Earth sort of wobbles on its axis, you can see it's tilted, this fluid doesn't stay rotating in a nice smooth way. Occasionally it tends to get disrupted or disturbed, and that causes a change in the magnetic field. And as you mentioned, the Earth's magnetic field is weakening. Over the last 2 centuries, it's been weakening at a rate of about 6% per century. And by the way, that number is accelerating, or that rate is accelerating. So
we're losing our magnetic field.
We are, and it's the rate at which we're losing it is increasing. The other thing that happens, which is quite interesting, is that the location of the North Magnetic Pole is not at the location of the North Geographic Pole. So the North Geographic Pole is right here at the top of the Earth, and that's the point around which we rotate in the north. The North Magnetic Pole is actually located somewhere in northern Canada, and it's slowly migrating towards Siberia. At the beginning of the 20th century, the migration rate of the pole was around 10 kilometers per year, or 6.2 miles per year. And currently it's, oh, well, I take that back. In 2003, it was migrating at about 40 kilometers per year, or 25 miles per year.
Boy.
And that too is accelerating. So it's moving more and it's weakening. And so eventually we will lose the magnetic field around the Earth, or some of it, and then when it reforms again or restarts, it will be flipped. So we will have our compasses will essentially point backwards.
So there would be a job for people. They could actually sit and watch their compass needle, and the compass needle, which normally points, that says north is that way, if they watched it long enough for a few thousand years, the compass needle would swing and point the other way. North would be that way. Does that mean the whole Earth is changing its geographic poles?
No, that stays put. Just the magnetic pole. And these reversals have happened many times. We figure it's probably about 170 times in the last 100 million years.
Whoa.
So now the last reversal was somewhere around 780 million years ago.
Jeepers.
Yeah, so the reversals happen, and they're random. There's no real pattern to their reversal. So we don't really know when they're going to happen, but we know it's going to happen again.
So we couldn't really write to our congressman and ask for some reversal and expect to get any action?
No, probably not. I don't know if they respond that quickly.
Oh, okay.
But
gotcha.
yeah, so the reversal will happen. One of the common questions I get from students when we talk about it is, well, what happens when there's a reversal? And no one really knows for sure, since the last one was 780 million years ago, or I'm sorry, 780,000 years ago. No one was around for that, so we don't know exactly, but some things that will occur, well, birds and turtles will have a harder time migrating. We probably won't notice too much as far as navigation goes, since we don't use compasses as much anymore. The other thing that will likely happen is we'll see some degradation of the ozone layer, because again, it will start to erode the upper atmosphere, and the ozone layer is one of those things that will be hit. And there's some question as to whether or not it could cause some changes or mutation to DNA, which could accelerate possibly evolution a little bit.
So we shouldn't really worry too much about it, because it's not going to happen for a few thousand years?
Yeah, at the current rate of decay, at least 1,600 years before we would have no field. Wow. And the other thing that's kind of fascinating is when this does happen, it's not that we have no field, it's just we have a weaker field. And instead of having two poles, the North Pole and the South Pole, we'll have multiple norths and multiple souths. So our compasses will be very confused.
Yes.
But we'll still have a bit of a magnetic field around the Earth.
Well, some of us are pretty confused already anyway. So.
That's true, and I'm there with them. So.
Well, Joe, I wanted to talk to you about something besides magnetism, although I think you've done a fabulous job in getting our viewers to see what magnetism is all about. But there's a lot more to this guy than magnetism. And I think we even have, see, I like to Google people. And so let's get the Google You up here for Joe, because Google You reveals something to me which is very interesting. Because the first thing that Google You came up with is ratemyprofessor.com. And ratemyprofessor.com has Joe rated at a 4.8 out of 5, which is fabulous, absolutely fabulous. So Joe, as a physics professor, really knows what he's talking about. But as you go further down the list, you find that the field is difficult, and but he's a very hot guy. Now, this one is an indicator of one of Joe's hobbies. Can you see this well enough? I hope on your TV. This is Joe. You're in a cave, aren't you?
That is correct.
Oh, wow.
Yeah, we found out about a cave system in the Upper Peninsula of Michigan.
Oh, wow.
Somebody told us it's about 100 meters deep, and it opens up into this cavern with a waterfall on the inside. We couldn't quite get back all the way. This was in the springtime, and with all the snow we had this past winter, it was still full of water. And, so we got back a little ways, but this is me going through a little tunnel trying to get out.
Right. What else we got? There's a good one. We got 2 minutes to wind this up, so Joe, you got to do this fast.
Okay, talk quickly. Yep. So this is New Year's Day, this past New Year's. I had some friends up from Texas, and the person in the boat with me is Ainsley. She is quite the paddler, and her sister Emily is in her own boat this day, who's also quite the paddler.
Did you say Ainsley was 4?
Ainsley just turned 5, not that long ago. So.
And here you are skiing.
Yes, this is in Tahoe, out there with a couple of friends of mine, snowboarding and some skiing out in Tahoe.
My gosh. And this one is?
Moab, Utah.
Moab, oh yeah, I've
doing
been
some
there
mountain
too.
biking out there, nice and warm.
Yeah, I'll say. And this is you climbing what looks like a glacier.
It's actually a frozen waterfall. Also in the Upper Peninsula of Michigan, near Munising.
Holy.
Yeah, a lot of fun.
Joe does so many things, and he does them so well, that it's a delight to have him come onto the program and explain just a little. Thanks an awful lot for coming by.
Thank you.
Sure appreciate it. I hope all you viewers have enjoyed this a lot. But until the next time I see you, I'm Art Wiggins.